Now let's examine the energy diagram of an SN2 reaction. Starting out with the starting materials. The oxygen will attack the carbon just like we showed you. So let me just quickly draw the mechanism here. Like that. Rising up the energy curve to the peak of the energy hump where the transition state exists. So the bonds are 50% made, 50% broken at this point. Now, of course, the transition state can cascade back down this way. It doesn't have to go to products, of course. They can go backwards in time. The OH could back out, the iodine could come back in, and you go backwards. But that's not interesting because that just goes back to where we started. What we want to do is go this way. So as it cascades down this way, this oxygen gets closer and closer to forming a bond with carbon, and this iodide gets further and further away. And that's how the mechanism works. It's a one-step reaction. One-step reaction. Now, it's called bimolecular because there's two different species in the rate-limiting step. There's only one step in this reaction. So right here, so that must be rate-limiting because there's only one step. And that in SN2, the 2 means bimolecular, which means it's a second-order reaction, which means there are two different species in the rate-limiting step, in the transition state. So the two species are the OH minus hydroxide and the methyl iodide. So they're there together in the transition state or in the rate-limiting step. This is called a concerted reaction. Concerted simply means happens at the same time. So the bonds are made and the bonds are broken at the same time. Okay? Bonds are made, bonds are broken at the same time. One more time. Bonds are made, bonds are broken at the same time. Its rate limiting step is second order. So the rate is second order. The alkyl halides concentration matters and the nucleophiles concentration matters. If I double the nucleophiles concentration, I double the rate of the reaction. If I double the alkyl halides concentration, I double the rate of the reaction. Okay, this is SN2. When dealing with an SN2 reaction, you want to consider nucleophilic strength. Strong nucleophiles will react faster. Now, the key and the kicker and kind of the problem with SN2 reactions is not really a problem, but more of the confusing part is that strong bases can be strong nucleophiles, but not all strong nucleophiles are basic. You have to consider, what does it mean to be basic? What does it mean to be a nucleophile? Well, bases are negative. Nucleophiles are negative, so they're both negative, or slightly negative, delta negative. The difference is this. A base, especially if we're talking about Bronsted bases, attack protons. So bases attack protons. So is a negatively charged thing more likely to attack a proton or more likely to attack a electrophile, pardon me. If it's more likely to attack a proton, that's a base. If it's more likely to attack something that's not a proton, that's a nucleophile. Nucleophiles attack anything but hydrogen or protons. Bases always attack protons. Bronsted bases, that is. Okay? So here are some strong nucleophiles. Sulfur S-, very strong nucleophile. Iodides, phosphorus, these things are very strong nucleophiles. Now as we go down, we get into the more basic ones. Now they are still strong nucleophiles, but they actually start behaving a little bit like bases. Hydroxide, for example, everyone recognizes that as a base, but it could be a nucleophile depending on how it's treated. Depending on the environment that it's exposed to, it could definitely go and attack a non-hydrogen thing. Methoxide, we're going to see that used a lot as a strong base. So it's one of these things where you kind of get a feel for it. Generally speaking, these things behave as bases before they behave as nucleophiles. And we'll get more into that in a minute. These are your moderate nucleophiles here, and these are your weak ones. So water, methanol, fluoride, acetate, weak nucleophiles. So essentially, just because you have a negative charge doesn't mean you're a nucleophile. You know, this, like for example, this one is resonance stabilized, so it's going to be, not very nucleophilic. Fluoride is not a very good nucleophile. Neither is chloride, really. Chloride and fluoride are not very good nucleophiles, although chloride is better than fluoride. And neutral molecules don't generally behave very well as nucleophiles. So as I was saying before, basicity is defined by the equilibrium constant for extracting a proton, so you have to attack a proton. Nucleophilicity is defined by the rate of attack of an electrophilic carbon. In organic, it's always a nucleophilic carbon. It doesn't have to be. It could be another atom, but it cannot be hydrogen. So this is the difference. No, so bases are nucleophiles. Nucleophiles are bases. What changes them and what makes them different is who they're attacking. Okay? Generally speaking, O minuses like to behave as bases. S minuses like to behave as nucleophiles. It's just a general concept. So some trends in nucleophilicity. A negatively charged nucleophile is stronger than its neutral counterpart. So for example, OH minus is a stronger nucleophile than water. Cyanide is a stronger nucleophile than its counterpart. This would be wouldn't even be nucleophilic, to be honest with you. Sulfur is a better nucleophile than hydrogen sulfide. For example, nucleophilicity decreases from left to right. So if we think about the periodic table, carbon, nitrogen, oxygen, fluorine, nitrogen is before oxygen in the periodic table. So you would expect NH3 to be a better nucleophile than water, and indeed it is. Now you would expect water, or should say, let's say OH minus, is a better nucleophile than F minus. Okay, so that's the trend in nucleophilicity. Nucleophilicity increases as you go down a group, pardon me. Nucleophilicity increases as you go down a group, as size and polarizability increase. So for example, sulfur, so say S minus, is below oxygen, so say OH minus. So this is a better nucleophile. Sulfur is lower on the periodic table. It's down one step from oxygen in the group. So sulfur is a better nucleophile. Another great example of this is iodide. Iodide is below bromide. Bromide is below chloride. So iodide is a better nucleophile than bromide. Bromide is better than chloride. Chloride is better than fluoride. Okay, so these things will behave more of nucleophiles as you go down the group. Make sense? That's because that's how it goes. Hopefully that makes sense, because that's just how it works. We're going to talk more about polarizability in a moment. Polarizability is one of the more interesting phenomenons in chemistry. At least I think it's interesting. The way it works is the larger a nucleophile, especially when you're dealing with atoms or ions, the larger the nucleophile, the more polarizable it is. So for example, fluoride versus iodide. Iodide is way down on the periodic table. Fluoride's way at the top. Iodide is much larger. It has more electrons. Its electron cloud is bigger. It's much larger. Its valence electrons are much further away than fluoride's. Fluoride's valence electrons are held very close to the nucleus. Iodide's valence electrons are quite far away from the nucleus. So I tell students to imagine the electron cloud as a swarm of bees. If your bees are held close to your hive, the bees are less likely to go out and attack anything. If the bees are quite far away from the hive, like they're held further away, they're more likely to go and attack things. Okay? So in my example, fluoride's beads, their electrons, are held close together to the nucleus. They're held tight. So this fluoride ion has to get very close to this carbon's electrophilic carbon with its back lobe of the sp3 orbital here. Remember, sp3 orbitals have a big front lobe and a smaller back lobe. So these electrons have this ion has to get very close to this carbon atom right here before these electrons can find their way over there to form the bond, because the electrons have to move away from the nucleus somewhat to get into that lobe of the sp3 orbital of carbon. So because fluoride holds it very close, holds its electrons very close, the whole ion has to get close, which means this nucleophile and this nucleophile, this nucleus and that nucleus in there have to get closer. So that's going to take time. Iodide, on the other hand, has its swarm of bees way out here. And those swarm of bees are like, hey, look at that. A positive charge is over here. A delta positive charge is right over here. And they're like, because they're not held that tightly by the nucleus. There's a positive charge here and there's a positive charge here. So this nucleus is positive. This nucleus is positive. So they're like, the electrons that are way out here are like, this is pretty attractive. And they go, and they attack. All right. Fluoride, on the other hand, they're like, well, this is positive and that's positive, but this positive is pretty gosh darn attractive. I'm going to have to get a lot closer to that positive to do a reaction. Okay? And that's polarizability. The more polarizable the electrons are, the more free they are to move, the less close they are to the nucleus, the more they are able to be attracted away to another positive charge or slightly positive charge. That's polarizability. I know it's a very abstract concept, but try to wrap your head around it because it's a very interesting concept. Just the fact that these electrons are further away means they can be attracted into an electrophilic carbon much easier. So they'll be more willing to be a nucleophile. I know that's complicated. I know that's abstract, but try to let your head kind of massage it a little bit, and you'll eventually understand it. It's really an interesting concept. Solvent effects, polar protic solvents versus protic solvents. Now, protic solvents are solvents that can hydrogen bond, more or less is how you say it. Common protic solvents are alcohols, water. Water, of course, is polar protic. And these solvents are not very good for SN2 reactions. And here's why. Say we have a nucleophile. Nucleophiles are either negative or slightly negative. So let's say we have a negative nucleophile. Let's say we have iodide. And say we want that iodide to attack this delta positive carbon over here. So we want this iodide to attack that carbon over there. That would be really good if it did that. Unfortunately, what happens in a polar protic solvent, because the hydrogen here is delta positive, this oxygen is delta negative, what happens is you get hydrogen bonding, or ion dipole bonding, if you want to say it that way, of this delta positive hydrogen to the iodide. And not just one. There we go. So you get the solvent surrounding the nucleophile. So in order for this iodide to attack that carbon, the solvent has to get out of the way. Now you have to remember that molecules and ions are not thinking. This iodide is not thinking, well, the guy who put me here wants me to attack that carbon, so I'm going to go do it. That's not what they do. The iodide goes into solution and gets surrounded by positive charges, slightly positive charges, delta positive charges. So the iodide is like, cool. That's nice, and kind of just mingles, hangs out with those delta positive hydrogens, because first of all, it's the solvent, so there's going to be a lot more of them. The solvent is always there in the greater amount because that's how solution chemistry is defined. So in order for this iodide to even know that delta positive carbon exists, it has to be able to get over to it. But to get over to it, it has to go through all these methanols that are surrounding it, and so these ones are here. Let's imagine this iodide finds its way a little bit further over here and pushes these methanols out of the way. Well, there's more methanols here. So it's going to slow the approach of the iodide down. It's going to slow the iodide down. It's going to make less collisions. Those collisions it does make to this carbon are going to be slower. You have to understand collisions and energy and angle are the three things that has to happen for a chemical reaction to occur. If this solvent sphere, or solvent cage as I call them, because it's more a cage, is stopping the nucleophile, is preventing collisions, is preventing reaction. So anything that prevents collisions slows reactions down. That's what polar protic solvents do in SN2 reactions. They slow the approach of the nucleophile, or they can completely prevent it. So we've learned that polar protic solvents are no good for SN2 reactions. So what do we use for SN2 reactions? Well, we have to use what are called polar aprotic solvents. These are polar solvents that don't have a proton or a hydrogen that can accomplish hydrogen bonding. So that way it can't set up a solvent cage as efficiently as a polar protic solvent will. Examples of this are like acetone, for example. That's acetone. DMSO. DMF, dimethylformamide. Acetonitrile. And those are just a few examples. There are other ones, but these are the top four big dogs. Sorry about that. I kind of messed this last one up. There we go. That makes more sense. So these are the big ones that most people choose right off the top because A, they're mostly readily available in most chemistry labs, and B, they work. They work really well. So historically, people have chosen them to do their SN2 reactions. So when you're looking at an exam question, you're wondering, is this reaction SN2 or something else? Look for the polar protic solvent. I'm sorry, look for the polar aprotic solvent. If it's polar protic, it's probably not doing an SN2 reaction. In fact, take it to the bank. If it's a polar protic solvent, it's not SN2. If it's a polar protic, start thinking very seriously about SN2. So far in SN2 reactions, we've talked about the solvent, and then we talked about the nucleophile. Let's now talk about the leaving group, because in any SN2 reaction, there's a nucleophile, an electrophile, and a leaving group. There's three different things. Leaving groups have to be stable in whatever solvent or environment they're in, or they won't leave. Okay? So that's the first thing. They have to be stable in the environment that they're in. So what I tell people is a good leaving group is the conjugate base of a strong acid. A good leaving group is the conjugate base of a strong acid. That's why chloride, bromide, iodide are all good leaving groups because they're all conjugate bases of strong acids. Hydrochloric acid, hydrobromic acid, hydroiodic acid. Here are some ones you may not be familiar with, though. These are the ones that kind of sort of look like sulfuric acid. Remember, sulfuric acid is this, right? Or I should say hydrogen sulfate is like this. So these two things are kind of similar in structure, right? Kind of similar. I didn't say they were the same. I never said they were the same. They're similar. So if this is the conjugate base of a strong acid, this probably is too. If this would be a good leaving group, this more than likely is too. These are both actually excellent leaving groups. This one is commonly used. An R can be methyl, trifluoromethyl. It can be a lot of different things. So these are good leaving groups. And we're going to see this a lot, this a little bit less so, and never ever going to see this in these classes. Now let's look at some neutral molecules. So water can be a good leaving group. We're going to see that in another unit where we do dehydrations of alcohols. Alcohols, of course, can be good leaving groups. If water can, alcohol can too. Nitrogen, ammonia, for example, can be a good leaving group. Nitrogen itself there's reactions where nitrogen itself will leave, and so on. So small neutral molecules are also good leaving groups. So look for a alkyl halide. That's a good leaving group. The alkyl halide has a good leaving group on it. All right, so now we spoke about the nucleophile, we spoke about the solvent, and we spoke about the leaving group. Now we have to move into the substrate, or the electrophile, the alkyl halide. The alkyl halide matters a lot. I can't overemphasize this enough. The alkyl halide matters a lot. Methyl halides react extremely fast. Methyl halides react extremely fast. Primary halides react fast, but slower than methyl halides. Secondary halides react slower, but at least they react. Tertiary halides, this is the key, write this down. If you're not writing everything down, write this down. Tertiary halides, third degree halides, do not react via the SN2 mechanism. Tertiary halides do not react via the SN2 mechanism. Tertiary halides do not react via the SN2 mechanism due to steric hindrance. The steric hindrance prevents SN2 reactions from occurring on tertiary halides. That's an important concept that you have to understand. Methyl reacts quick, primary reacts fast, secondary reacts slow but does react, tertiary does not react in SN2 mechanisms. So let's take a look at this chart. The first thing I want to draw your attention to is this secondary halide, and we're going to say that has a reaction rate of 1. So everything is going to revolve around this reaction rate. So let's just say this particular halide will react in a reaction 1 per second. Okay? So if this one reacts 1 per second, and this is secondary. Primary will react 50 times faster. So secondary versus primary, 50 times faster for primary. Methyl will react 1,000 times or more faster than secondary. So methyl is very fast. Primary, not quite as fast, but still pretty good. Secondary is our reference point, so it reacts as 1. Now look at tertiary, less than 0.001 per second. So it's essentially not reacting. Now, this is a primary one, though. This is a primary one. So why isn't it reacting at 50? See, primaries were here. They're reacting 50 times faster than the secondary. Primary is slowing this down. Look at this, 20. What slowed it down? Well, the fact that this chain got longer. Any bulk that can block the access to this carbon, any bulk over here that can block access to this carbon will slow the reaction rate down. So look at the next one down. So here's the carbon that has to be attacked. Notice there's a bunch of bulk out here now. There's branching going on out here. And the reaction rate went down. It went down quite a bit. From 50 for a primary all the way down to a 2. Now it's still primary, technically defined as primary, but now there's a lot of bulk out here. So check this one out. This is still technically primary, but now there's still a lot of branching going on just outside of the primary carbon, right? And look at the reaction rate. Slow, very slow. So the take-home message here is primary does react quick, but it still depends on bulk. What's behind the electrophilic carbon? If there's a lot of bulkiness out there, a lot of branching, that's going to slow down SN2 reactions. Okay? So that's the take-home message here is have your electrophilic carbon freely accessible to the nucleophile. If the nucleophile runs into any obstacles, it will react a lot slower. Think about it as, someone trying to run through a room and there's nothing in the room. They can run from one wall to the other rather quickly. Now, take some chairs and tables and put them in the room in random order. Blindfold the person. Tell them to run to the other wall. Well, they're going to have a harder time because they're going to start running into obstacles. Same thing's happening in an SN2 reaction. The nucleophile is trying to get to the electrophile, essentially trying to run from one side of the room to the other. If there's no obstacles in the way, it can happen very fast. If there's obstacles in the way, the nucleophile is going to bounce off of them. It's going to bounce in all directions off of that bulk. And that's what's happening here. Even though these are primary, the bulk is still slowing down the nucleophilic approach occurring inside this reaction. That bulk is such a big deal. So let's say a reaction that works fast, methyl. And NUC is generic nucleophile. Doesn't matter what NUC is. So now this nucleophile, let's say it's negative, has to come in and attack in a situation known as backside attack. Backside attack. The nucleophile must approach from the side opposite the leaving group. It can't approach any other way. It has to come in here. Now remember, SN2, or sorry, sp3 orbitals. I can do a little better. sp3 orbitals have this little lobe back here. The nucleophile has to enter that lobe. The electrons have to go into that lobe to cause a bond to occur. So it has to come in from behind the bromine because that's where the lobe is, first of all. Second of all, the bromine is delta negative. This thing is negative. It's going to be repelled by it. So the further away the nucleophile can get, the better. Okay? So the nucleophile must come in from the backside. So anything that prevents this approach, anything that prevents the nucleophile from coming into the backside will slow this approach down. Okay? Imagine, if you will, well, we'll get to it. We'll get to it in a second. So let's do primary. Here we go. So here's our nucleophile. And it has to get in here. Attack from the back side, right? Has to get in here. Well, now we have this methyl group throwing some bulk in here. So these hydrogens are actually sticking down into the path. So the nucleophile needs to approach from here. These hydrogens are actually sticking down close to that path. So there's a good chance as this nucleophile is trying to line up, it's going to slam into this. Okay? And just think of this as a guard dog or a guardian standing in the way of the prize. So imagine, if you will, this is the goal in soccer or hockey. This is the goaltender. He's getting in the way. So there's a goaltender standing in the way of the nucleophile's approach. The nucleophile is not going to hit the target as often. So the reaction is going to slow down. Let's keep going. Let's imagine that we had secondary. So things are getting big. It's even getting messy to draw. Now, I think everyone will agree. Now the approach to the electrophilic carbon, remember, it has to get here. It has to get there where the delta positive is. I think everyone will agree the approach now is even more hindered. It's even more hindered just by the mere fact that these methyl groups or these alkyl groups or groups are there. They're big. They're getting in the way. So now let's draw the tertiary halide, the one that doesn't work, and let's see how bulky it can get back there. I think everyone's kind of seeing where I'm going with this. So there's the bromine. Oops, not hydrogen. As you can see, it's even hard to find room to draw anything. It's just bulky, bulky, bulky. And I had to even switch to red so I can at least see a little bit of things going on here. So now from here, you can see if the nucleophile tries to get in there, put an X on the arrow to mean it just doesn't happen. It doesn't work. There's not enough room for the nucleophile to get in there. Now, don't forget, we draw these atoms as ink on paper, right? Or digital art on paper, however you want to say it. Remember, these things are really balls of electrons, right? They really have van der Waals radii and all that kind of stuff. So there's no room here at all. This carbon is completely sheltered from that nucleus, the nucleophile. This nucleophile will never get in there. There's just no possible path for it to take. So the keys here: backside attack must occur. Remember, to have a reaction, you must collide with enough energy in the right orientation. Well, the orientation in this reaction is backside attack. If you can't accomplish the backside attack, the reaction simply will not work. And that's the key to this reaction, is you have to have a nucleophile that is nucleophilic enough to get in there, an electrophile that's not bulky and can actually allow attack to occur. Now, stereochemistry of an SN2 reaction. SN2 reactions have an interesting phenomenon called Walden inversion. In a Walden inversion, essentially what happens is the stereochemistry flips. It's called inversion. Stereochemistry will invert. The absolute configuration will invert. Now, let's see that in practice. And let's use, I don't know, cyanide, I guess. Cyanide's going to attack there. The bromide's going to leave. Nothing unique here. Everyone kind of already knows this. So the transition state something like that. And now, if we continue on, we're going to have this molecule. There, let's write CN to make it neater. So now what's happened here? Notice how the ethyl and the methyl and the hydrogen are all facing towards the cyanide. So now as the cyanide comes in, the electron density from the cyanide comes in. Remember, these lines and these dashes and wedges that I've drawn are just representing pairs of electrons. They're representing pairs of electrons. One more time. The lines and dashes and wedges represent pairs of electrons. So as this pair of electrons comes in to make a bond, these electrons are repelled by it, right? Don't forget, these are electrons in here. These electrons are repelled by these two. So as these two come in, these two repel away to form this structure right here, this transition state structure. Okay? So as this bond forms, these electrons from the cyanide get closer and closer and closer. The electrons from the bromide get further and further away. These electrons in the bonds here will go this way. Okay? That's what they'll do. It's all because of electron repulsion. It's all Vesper theory. Electrons come in. These electrons get repelled and go away from it, forming this transition state, which now as this bond forms, the cyanide, the nucleophile electrophile bond forms, these electrons are going to face the opposite direction. And that's an inversion. That's a Walden inversion. It's known as a Walden inversion. Okay? And that's what it is. That's what a Walden inversion is, and that's why it occurs. Okay? A lot of times you'll end up with the opposite configuration. You go from R to S or S to R, but not always.